In this problem, we're going to be working with a couple things. We're going to be working with some stoichiometry, and we're also going to be working with partial pressure. So this is going to be kind of an involved problem. So let's read through it. In a collision of sufficient force, automobile airbags respond by electrically triggering the explosive decomposition of sodium azide. So this is sodium, and azide is going to be N3 to its elements. A 50-gram sample of sodium azide was decomposed, and the nitrogen gas generated was collected over water. So they're trying to determine, if you have 50 grams of sodium azide, what is the volume of nitrogen that's going to be released from 50 grams of azide. In order to do that, you have to do a water displacement experiment. And so they want to know how much sodium azide should properly be put into an airbag such that it isn't too voluminous and it isn't too small. All right? They want it to be just the right size, such that unfortunately during a collision, the occupants will survive. And so they're going to collect this over water. So that's how you would measure the volume of the nitrogen. The pressure was 745.5 millimeters of mercury. So that's going to be the total pressure. And how many liters of dry nitrogen was generated? So for the first part, what we want to do is we want to write a balanced equation. We won't use it right away, but we want to get to the balanced equation for this. So it's going to be 2 sodium azides produces 2 sodium, this is going to be a solid, plus, that'd be 6, that would be 3 moles of nitrogen gas. We'll get to this in a few minutes because we'll have to do some stoichiometry to go from 50 grams of sodium azide to the moles of nitrogen. So to start out with, we know that the initial temperature is going to be 26 degrees Celsius. That is equal to, we might as well convert that into Kelvin right now. That's going to be equal to 299.15 Kelvin. Now, we're not going to convert the pressure quite yet. We'll do that in a few minutes. We're not going to do that quite yet because the pressure total, which is what this is the pressure total, is equal to the pressure of the nitrogen plus the pressure of the water, and this is going to be at 26 degrees Celsius. So we're looking at the vapor pressure of water when it's 26 degrees Celsius. All right. You can look this number up in a table. So the vapor pressure of water at 26 degrees Celsius is equal to 22.4 millimeters of mercury. And you can get this from a table. So I looked this up on a table is where I found this. This isn't something I would expect you to know. This would be a value you would look up on a table or on the internet. Therefore, the pressure of the nitrogen is equal to the total pressure minus the pressure of the water at 26 degrees Celsius. Now, I don't typically always write 26 degrees Celsius. I'm just doing this because this pressure does change with the temperature. And this will be equal to 745.5 millimeters of mercury minus the 22.4 millimeters of mercury, giving us a pressure of 723.1 millimeters of mercury. Now, if I convert that into atmospheres, 1 atmosphere is equal to 760 millimeters of mercury. The millimeters of mercury cancel, and what I end up getting is I get 0.951 atmospheres. And that's going to be of just simply the dry nitrogen. We're going to use that in a few minutes, all right? Now, let's work with what's determined the number of moles of nitrogen that are going to be evolved from the 50 grams of sodium azide. So we start with the 50.0 grams of sodium azide. We convert that into moles. 1 mole of sodium azide is equal to 65 grams of sodium azide. And once again, this number comes from the periodic table. We then see that the mole ratio is 2 to 3. So for every 2 moles of sodium azide, we get 3 moles of nitrogen. So that cancels, and the number that we get is, yes, it would be 1.154 moles of nitrogen. All right, now we can use our ideal gas law. And what we're looking for is we're looking for volume, right? And so volume is going to be equal to nRT all upon P. And so our volume, our number of moles of nitrogen is going to be 1.154 moles times R, which is 0.08206 liter atmosphere mole Kelvin times our temperature, which is 299.15 Kelvin. And that's going to be divided by the pressure of the nitrogen gas that we found down there. So that'd be 0.951 atmospheres. Our atmospheres cancel, our kelvins cancel, our moles cancel, and we're left in units of liters. And this is going to give us 29.77 liters of nitrogen gas. Now, the reason we went through this entire pressure over here, I want to go back to that a little bit, is because when you are collecting a gas over water, and what happens is you would take for instance, a graduated cylinder or some type of vessel, you'd fill that with water, and then you'd run a hose into that vessel, and then that hose would also be connected to the reaction flask. As the nitrogen is being evolved, it is going to displace that water. But what's going to be in that flask is, yes, it's mostly going to be nitrogen, but there's also going to be just a little bit of water. So we want to get rid of that amount of water when we actually do the calculation, such that we can determine the total pressure of just simply the nitrogen and the nitrogen alone, not with the water in it. And if we have 50 grams of sodium azide and we allow it to react or decompose, it's going to generate 29.77 liters of nitrogen gas. If you have any questions on partial pressures or stoichiometry or the ideal gas law, please let me know.